Okay, so, all right, so this is chapter 8. We're going to do logarithmic functions, and these are all the outcomes in this chapter. Okay, so we just finished doing the investigation for understanding logarithms, so we're just going to get into these notes here. So the logarithmic function is the inverse of the exponential function. Remember, to find the inverse of a function, we switch the x and the y values, and then we solve for y. So this is the exponential function here, and this is the inverse function. And you notice the differences that we've switched the x's and y's. Now, notice that the y value is now an exponent in the inverse function here. So in order to isolate and manipulate exponents, we must use something called the logarithmic function. So here we've got y equals log base b x. So b is the base of the log. If there isn't a base written, if you just see something like log of x, then that means, if this is missing, then it means that it's base 10. Okay? All right, so for this here, it says y equals 2 to the power of x. So we want to see the graph of this and the inverse. So the graph of y equals 2 to the x, let's draw a little table of values. So if we have x and we choose 2, 1, 0, -1, -2, what are the corresponding values for 2 to the power of x? So this is 2 to the power of 2, which is 4. 2 to the power of 1 is 2. 2 to the power of 0 is 1. 2 to the power of -1 is 1/2. 2 to the power of -2 is 1/4. Okay, so we graph that, and we end up with, so -2, we get 1/4. So let's say that's here. -1, we get 1/2. That's there. 0, we get 1. That's here. 1, we get 2, and then at 2 we get 4, which is off the graph, but you get the idea of what's happening here. So we can, whoops, make it look like that. This is what happens here, folks. This is a asymptote right here. So we've got y equals 0 as our asymptote. Okay, I should label this graph so we know which one we're talking about, 2 to the power of x. And then our inverse, so let's do a little table of values here. So yeah, so you're just switching the x's and y's. Actually, yeah, so let's just do a reflection over the x equals y and get this as our, so we'll just do a reflection here, much quicker to graph it that way. Okay. All right, and so where is the asymptote going to be for this guy here? On? X equals 0, yeah. Okay, so that is y equals 2 to the power of x. That's the inverse. All right, so the equation of the graph of the inverse is y equals log 2x. So the graph of, okay, so this one is going to be, this is the inverse of y equals 2x. So I should actually label that as x equals 2 to the power of y. Is that better? Yeah. Okay. All right. Okay. So note that this equation is going to result the same graph as what? Yeah, as y equals log 2x. And we saw that in our investigation as well, right? Yeah. Okay. So now example 2 on the next page says express m to the power of n. Express m equals 4 to the power of n in log form. So let's write down our exponential form here, just so we have it handy, and then our log form here, so that we have it for reference. We don't have to keep flipping pages back and forth. So we've got y equals log base b x. So x is our argument there. All right, so what's, this is going to be the argument. So we're going to end up with log. So what's our base here? 4. And then it's going to be m equals, and then what is it going to be equal to? The exponent of here, so n. And then express log base 2, 8 equals 3 in exponential form. But one thing I want you to kind of think back to the investigation we did. What is 8 equal to? 8 is equal to 2 to the power of 3, right? So that kind of helps us remember what we've got. And then 2 to the power of 3 is equal to 8. And well, there you go. Our thinking of what it actually means translates exactly to what the values are. Okay, so this is exponential form. And we know that this is true, right? Okay, so evaluate the following expressions. So if we evaluate means that we need an actual number as our answer. So this is going to be, yeah, you could think of it as 2 to the power of x equals 16. What is the value of x that's going to satisfy this? So 4. We know that 2 to the power of 4 is equal to 16, so x is equal to 4. Okay, so here we need, if we're evaluating, we need to figure out what x is, right? That's basically what we're doing, is figuring out what this number is. So if I write it in exponential form, it'll kind of help me figure out what I'm doing. So what value of x is going to make this happen? Well, I'm going to need a negative power of x, right? So that it switches into the denominator, and then what is that power going to be? Yeah, so 2 to the power of negative 2 is equal to 1/4. We know that. So we can say that x is negative 2. And then here, for this last one, we have log base 3 of negative 27. So let's say that's equal to x. What we need to figure out is 3 to the power of x equals negative 27. So what value of x is going to make that happen? There isn't one. It's not possible, right? Because, well, you could think, okay, what is 3 to the power of 3? 3 to the power of 3 is 27, right? Now, what if I had a negative exponent? What is that going to do? It's gonna be 1 over 27. Is there any way that I could get a negative number out of there? No. So because it's negative, it's not possible. Not possible. So there's no solution. Okay? All right. So we can say that log base b a equals c, where a is greater than 0, b is greater than 0, and b does not equal 1. We've got the base of the logarithms, so note that the base of the logarithms cannot be negative. They're always positive. And then the argument a, which is right here, of a logarithm is always positive. So if we get a negative value in here, we get into trouble. Okay, so now example 5, we've just got some more equations to solve. But now what we're solving for is that x right there. Okay, so let's write that into exponential form, and that'll help us figure it out. So what can we write? We can write x to the power of 1/2 is equal to 5. So what value is going to allow us to get 5 from here? Okay, so what can we do to both sides of the equation to help us figure this out? So if I were to square it, square both sides, what would that end up giving me? 1/4. So if I square both sides, then I end up with x is equal to 25. Okay, and then let's verify that. So what is 25? 25 to the power of 1/2. That's the same as writing the square root of 25, right? And then what is the result of that? 5. So do I end up back at what I should? Yeah. So I'm okay. Okay. Now, let's say, for example, this wasn't 1/2, it was a 1/3. What would I do to each side? Yeah, you'd cube it, right? So you'd do the whatever's, if this is whatever number is in the denominator here, you would raise it to that power on both sides. Okay. Now, remember here what I said about a missing base? So there's no base written there, so what do we imagine it is? 10, right. So invisible base means that it's 10. So I could rewrite it for myself and go log base 10 x equals -3. So what am I trying to figure out? 10 to the power of -3 equals x. And then what do we get for x? X equals 1/1000. Okay, and if you want to check, if you want to just kind of check and double check for yourself, because in the investigation we had a lot of practice with these types of equations where we had to evaluate. If I were to figure out the log base 10 of 1/1000, does it give me -3? And it does. So because it's 10 to the power of -3, this is 10 to the power of -3 over here. Okay, so now just remember, when the base is not indicated, it means that it's base 10. All right, now we've got bases. We've got a base of 16 here. So let's rewrite it in exponential form. What do we end up getting? 16 to the power of 3/4, and that is equal to x. Do you remember what this power of 3/4 means? How can we rewrite it so that it kind of makes more sense in terms of numbers to us? I'm going to give you a hint. It's a root of some sort. Which root? The 4th root of 16 cubed. So that's equal to x. We're trying to figure this out. Well, how can we break down 16? What is 16? What if I wrote it as a base 2 number? What could I say it is? So 2 times 2 times 2 times 2 is equal to 16? 2 to the power of 4 equals 16, right? Okay, and then so 2 to the power, so let's just kind of have an aside bubble here. So if I write 16 as, so I've got, oh, hang on, 2 to the power of 4, and then to the power of 3, and I am 4th rooting it. Is that a little easier to swallow in terms of what I'm doing here? Yeah? Okay, so what does it end up being then? What is this result? I've got a 4th here and a 4th root here, so this is 2 to the power of 3. All right, so what is So since this is equal to 2 to the power of 3, what can I say the value of x is? Yeah. So we kind of had to break 16 down so that it was a little bit easier for us to work with. All right, and now here we've got a log and then a log inside. What is this inner part equal to? So let's let y equals what's in here in the bracket. So log 3, 81. And now we can actually evaluate what it is. So we've got 3y equals 81. So what is y equal to here? 4, because 3 to the power of 4 is 81. Okay, now I can rewrite the question as log 2 and then 4 equals x. And then I can evaluate this. So that is 2 to the power of x is equal to 4. What is x equal to? 2. Perfect. So sometimes you have to just kind of put it in terms of something that's easier to work with. And when you've got a log in a log, evaluate what you can, and then work from the inside outwards, just like in order of operations. All right, now for example 6, we're going to estimate the following values. So let's not use a calculator and let's try to do these questions. So it's log base 2 equals 30. So that's the first one here. Well, let's say that it's equal to x so that we can rewrite it in exponential form. So 2 to the power of x is equal to 30. Well, what do we know? We know we know 2 to the power of 4 is 16, and we know 2 to the power of 5 is 32. So we know our answer is going to be between 4 and 5. But where is it closer to? Which one is it closer to? So it's closer to this one, right? So maybe you could estimate something more than 4.5, right? So like let's say 4.8 or 4.9, okay? And then if you were to use your calculator, you can see which one it's closer to. But that would be a reasonable estimate. And then log of 20 here, what do we remember about what log and an invisible base is? So we can rewrite this as log base 10, 20 equals x. We want to figure out what x is. So if I write it in exponential form, I can kind of think and guess through it. Well, what do we know here? We know 10 to the power of 1 is equal to 10. What's 10 to the power of 2? It's 100. So where is our answer going to be closer to? It's going to be closer to this one here, right? So we can say it's going to be somewhere between 1 and 2. So we can estimate closer to the 1. So we can say x is equal to 1.2 approximately, or 1.3. So those would be reasonable answers. And then the last one here, we've got log base 5. So let's say that's equal to x. Rewrite that in exponential form. And that's between 25 and 125. So our answer, again, is going to be between 2 and 3. So we could estimate, which one is it going to be closer to? This one here. So we can say x is approximately 2.9 or so, and that's really close, right? So the actual answer here is around 2.97. So that's a really good estimate there. Okay, so there's the homework here. So make sure you guys do the homework. And that's all for today, folks.